All right, let's estimate the area under a curve using a Riemann sum. But first, let's review what we know already. Okay, before we used a rectangle to make an estimate. So let's say we have a function f of x that gives the number of mice that move into the basement each day. And we're going to enclose this in a rectangle. So the height of this rectangle is 20 mice per day. That's this height. And the width of the rectangle is 12 days. So this entire rectangle is 20 times 12, or 240. But we want to estimate the part of the rectangle that's under the curve. So this would be about half. So I'm guessing it's about 60% of that. So 60% of 240 is 0.6 times 240, which is 144. So that's just an estimate or an educated guess. Let's talk about the units of this answer. So the height is mice per day. The width is the number of days. So we've multiplied mice per day times the number of days. The days will cancel, and we end up with mice. So our estimate is, and I'm going to use approximately equal, 144 mice. So we would say from day 0 to day 12, 144 mice moved into the basement. So the area under that graph tells us how many mice moved into the basement from day 0 to day 12. I want to be very careful and point out that this is not the number of mice that are in the basement. We would need to know how many mice were already in the basement on day 0. This tells us how many new mice there are in the basement. So if there were already 100 mice on day 0, then on day 12, there would be 244. But we would need to be told that. You can't get that from the graph. All right, so we've been doing a lot of examples where the graph of f of x is above the x-axis. What does it mean if the graph of f of x is below the x-axis? So if the graph of f of x is below the x-axis, that means the values of f of x are negative. So if we're looking at mice per day for a certain number of days, reading this graph on day 0, negative 5 mice per day means that 5 mice are moving out each day, and that on day 8, 10 mice are moving out of the basement each day. So day 0, mice are leaving the basement at the rate of 5 mice per day. On day 8, mice are leaving the basement at the rate of 10 mice per day. All right, let's estimate the area and see what it tells us about the mice. So we're going to use a rectangle. We have a rectangle whose height is -10, but since we're finding an area, that would be 10, and whose width is 8. So the area of the entire rectangle is 10 times 8, or 80. And then we want to estimate what percent is in this shaded region. And let's say it's about 70%. So 0.7 times 80 is 56. But because we're multiplying a negative, it's going to be -56. Once again, we're multiplying mice per day times the number of days. So this means that 56 mice have left the basement. So from day 0 to day 8, 56 mice left the basement. And again, we don't know how many mice that leaves us with unless we know from another source how many mice we started out with on day 0. All right, let's talk about this definition for a moment. A monotonic function is a function that is either only increasing or only decreasing for a given interval. And why would we care if a function is monotonic? Well, when we're finding a Riemann sum, we can only find the error if the function is monotonic. So what are we going to do if the function is not monotonic? So if we want to find a Riemann sum and know our error using this function, is there a way we could make it monotonic? Well, this function is only increasing until this point. From here until here, it's decreasing. And then from here to here, it's increasing. So in order to find the Riemann sum and to know the exact error, we would break it up. You could find the Riemann sum from A to B, and then find the Riemann sum from B to C. And I know you're thinking, wait, this is negative, but it's still monotonic. This is only decreasing. So find this Riemann sum, and then find this Riemann sum. All right, let's introduce some notation. All right, so we want to find the Riemann sum. We want to estimate the area bounded by f of x and the x-axis for this interval between A and B. Well, first we're going to decide how many intervals we're going to use. So we'll call that n. The size of each interval is going to be called delta x. And to find delta x, we just take the size of our interval and divide it by the number of intervals. All right, when you get farther along, A, your left bound, is going to be called x0, and B, your right bound, is x sub n. And this is the same n. which is your number of intervals. So suppose the number of intervals is 4, then your left value of x is x0, the right one is x4, so this is x1, x2, x3, and this is the notation you'll use when you're taking calculus. Now, for the Riemann sum, we're going to find the area of these 4 rectangles. So in order to find the area, we're going to multiply the width, which is delta x. Remember, that's the size of each interval, times the height. So if our function is f of x, what's the height here? Well, you're just going to plug x0 into your function. So that height is f of x0. The height here, f of x1. This height, f of x3. And then this height is f of x4. All right. All right, what's the difference between the left-hand sum and the right-hand sum? So let's say we want to make this estimate of the area bounded by the graph and the x-axis between x0 and x2. So we have 2 rectangles that we want to draw. What does it mean to use the left-hand sum? Well, let's look at this first interval. The left bound is x0, the right bound is x1. When we do the left-hand sum, we use the height from the left. So we would use this rectangle. So the height is f of x0, and the width, as always, is delta x. For the next interval between x1 and x2, are we going to plug in x1 or x2? If you said x1, you would be correct. So when you're doing the left-hand sum, your Riemann sum is f of x0 times delta x. That's the area of this rectangle, plus f of x1, that's this height, times delta x. All right, let's do the right-hand sum. So for the first interval, which height am I going to use? F of x0 or f of x1? What do you think? If you guessed f of x1, you would be correct. So the size of the interval is delta x. That's the width. The height, we're going to use f of x1. So we're going to multiply that height times this width. And then for the next interval, which goes from x1 to x2, are we going to use the height from x1 or x2? If you said f of x2, you would be correct. So it's the height, f of x2, times the width, delta x, and that's the area of this rectangle. All right, this is a monotonically increasing function. One of these Riemann sums is an underestimate, and the other one is an overestimate. Which one do you think is the underestimate? If you said the left-hand sum, you would be correct. And this one would be an overestimate. All right. So if it's a monotonic function, we can find the error. The error is just the overestimate minus the underestimate. I'll write that down for you. We have our overestimate. To take away the underestimate, remember that you distribute this minus. So these terms will cancel out. We get f x2 minus if we factor out the delta x, and it turns out this is our B, that's our A. That's f of B minus f of A times the size of the interval. So it turns out your maximum possible error always depends on the size of your interval, because the height of the beginning of your function and the height at the end of your function don't change. So you can choose the acceptable error by choosing the size of the interval. We'll do an example in a minute. Let's do an example with an actual function with some numbers. All right, suppose we have the function f of x equals 3 plus 1/2 x squared, where x is the number of days since the start of flea season, and f of x is the number of fleas that jump on the cat, and that's fleas per day. So we want to estimate the area under the curve using a Riemann sum. Let's let n equals 4. Let's say we're going to use 4 intervals. And we're going to go from 0 to 8. So my starting value of x is 0. My ending value of x is 8. What's the size of each interval? That's delta x. So it's going to be 8 minus 0 divided by 4, which is 2. Let's draw in my intervals. 4 intervals, and they're each have a size of 2. So I start at 0. This will be x equals 2, x equals 4, x equals 6, and x equal to 8. Then I want to find the height. So I'm going to plug each of my x values into my original function. So f of 0 is 3. F of 2, 2 squared is 4. Half of that gives me 5. Plug in 4, 4 squared. Half of that plus 3 gives me 11. Plug in 6, 6 squared. Half of that. We get 8 and 35. All right, let's find the left-hand sum and then the right-hand sum. So I'm going to draw the left-hand sum in here first. Oh, and before I draw it, let's let you guess. If I'm using the left-hand sum, do I get the height from the 0 or from the 2? If you said 0, you would be correct. So this is a monotonically increasing function. So the left-hand sum is going to be the area of these 4 rectangles. And is that going to be an overestimate or an underestimate? If you said underestimate, then that's correct. So the size of each interval is the width of the rectangle, so that's 2. I'm getting my height from the left, so this height here is 3. So we're going to have 3 times 2, that's the area of this rectangle, plus, and then here, do I use the 5 or the 11? If you said the 5, that would be correct. And here I'm going to use the 11 or the 21. That's right, we're going to use the 11. And then for this interval, do I use the 21 or the 35? That's right, we use the 21. Put that all together, and we get an underestimate of 80. We're multiplying the height, which is fleas per day, times the width, which is fleas. We get an underestimate of 80 fleas. So that means from day 0 to day 8, at least 80 fleas jumped on the cat. All right, let's do the right-hand sum. I'm going to draw this graph again, just so it's not too messy. Oh, and before we go on to the right-hand sum, remember from day 0 to day 8, at least 80 fleas jumped on the cat. That doesn't mean that the cat has 80 fleas. You would need to know how many fleas it started out with, but this is the number of new fleas. And because it's the underestimate, we can say that's the minimum number of fleas that jumped on the cat. All right, let's do the right-hand sum. All right, now we're going to find the right-hand sum. That means for each interval, we're going to use the height from the right. So going from 0 to 2, we're going to use this height, which will be finding the area of this rectangle. For the second one, we're going to use the height on the right-hand side of the rectangle. So is the right-hand sum going to be an underestimate or an overestimate? If you said overestimate, that would be correct. So are we going to use the height of 3 or the height of 5 for this first rectangle? If you said 5, that would be correct. And we have the same width. So the area of the first rectangle is 5 times 2. The area of the second rectangle, we're going to use the height of 11. For the third rectangle, we're going to use the height of 21. And for the last rectangle, we're going to use the height from the right, which is 35. So the area of these 4 rectangles added together is 144. We're multiplying fleas per day times the number of days. So the days cancel. And this is an overestimate of the number of fleas that jumped on the cat from day 0 to day 8. So let me write down that sentence. Remember, because this is the overestimate, that's the maximum number of fleas that could have jumped on the cat. So from day 0 to day 8, no more than 144 fleas jumped on the cat. Again, this is not the number of fleas that are on the cat. We would need to know how many fleas the cat started out with. So we have our underestimate of 80 and our overestimate of 144. That means that we can now calculate the maximum possible error. So let's do that. Remember, it's only possible to find the maximum possible error because this is a monotonic function. And we simply subtract the underestimate from the overestimate. and we get 64 fleas. So let's say that's an unacceptable error, and you wanted to find a smaller error. How would you do that? Well, you can pick whatever error you find acceptable and then calculate the number of intervals you would need to achieve that smaller error. Let's do that one together. All right, so the error for a monotonic function is the maximum height, which is 35, minus the minimum height times the size of the interval. So previously, when we had 4 intervals, we ended up with an error of 64. If we want a smaller error, we need more intervals. So let's say we would only be happy if our error was equal to 2. We had the number of fleas correct within 2 fleas. So we're just going to say 2. So we're going to find the size of the interval. F of B is 35. F of A is 3. We got 32 times delta x. Divide both sides by 32 and reduce. So we would need the size of each interval to be 1/16. All right, what if we wanted to know how many intervals that would be? Remember that the size of our interval is b minus a over n. We want the size of our interval to be 1/16. B minus a is 8 minus 0. So 1/16 is 8 divided by n. If we cross multiply, that means we would have to have 128 intervals in order to get an error that's equal to 2 fleas.